thank you very much for the very kind invitation, very kind introduction, and it's a real pleasure to be here. I've been here only a few days, but I've enjoyed my time very much, and hope to come back again in the near future. So I didn't realize my mistakes would be recorded for posterity, so it makes me a little nervous, but okay. So I hope you forgive me any inaccuracies in what I present. Especially because what I want to do is mainly a historical presentation. So rather than go into technical details, I wanted to give some background. And so some of the dates I was not really able to find, but we'll see. We'll make some approximations. So we start maybe not so far back, but in the beginning of the talk anyways, we start, as the title suggests, with Algebraic K Theory. Okay, so this seems to be an invention of Grothendieck. Just the idea of K theory as the so-called Grothendieck group. So you take the category of, you take some variety or topological space, and then you take some category of vector bundles over X, or maybe if it's an algebraic variety, you can also talk about coherent sheaves on X. In any case, in both of these situations, you have the notion of, this is sort of has a notion of exact sequences built in. And so you can make a, whatever these categories are, let's call it, it's a category C with some exact sequences. And then you can form the Grothendieck group of C. You just take the free abelian group on the classes, the isomorphism classes, let me write down an isomorphism class E of objects E and C, and then modulo the following relation that you say a class E minus class E prime minus a class E double prime, yeah, should be 0 if there exists an exact sequence 0 to E prime to E double prime. Okay, so pretty much, I mean, these are the common situations where this arises. Oh, but you can imagine many other situations, so it's obviously a very powerful construction. So I guess this is somewhere in the early 50s, but I couldn't find an exact reference for this. So early 50s, maybe.
If my variety X is just a point.
Mm-hmm.
If my variety X is just a point.
Yeah.
What will be K naught of C?
Ah. Yeah, C is then, it depends what it is. C is, say, vector spaces over a field, if you like.
Yes.
Yeah, then it's just the integers by the dimension. It's an example. Yeah, so maybe it's an example, good example. C equals the category of vector spaces over a field F. Then K naught of C is isomorphic to the integers. Well, you send a vector space to its dimension, and then n times a vector space, because it's in an abelian group, so you can take n times any element, goes to n times the dimension, so essentially by dimension.
Probably you should say finite dimensional vector spaces.
Yeah, finite dimensional. Thank you. By dimension. Okay, good. So then there are some dates that I could find. Well, when you try and, so you then want to compare what happens on some x and some y. So you introduce a morphism, or let's say x to a point. And you have this notion of global sections and higher cohomology. So you can associate to some vector bundle E, you can associate the element in this free abelian group, you can associate to it the alternating sum of the cohomology groups on X with coefficients in E. So point, let's say this is a compact complex manifold, and point being just C, so these become C vector spaces. And so this becomes an element. This starts out with a vector bundle, so you can think of a class actually in K naught of X, going to a class in K naught of C. X is a complex manifold, and this we know is Z. So-called Sheaf-Euler characteristic. And so Hirzebruch found a formula for this. So chi of E has found a formula in terms of topological invariance. The so-called Hirzebruch-Riemann-Roch formula.
So do you need compactness?
Pardon me?
Your X has to be compact?
Yeah, as I said, compact complex manifold.
Okay.
Yeah. So Riemann-Roch, so-called Hirzebruch-Riemann-Roch. Of course, he didn't write it in terms of X sitting over a point because he just says, everything sits over a point. So he just says you have a compact complex manifold. And what can you say about this operation? But then Grothendieck looked at the situation, so that's Hirzebruch, and then Grothendieck, say with Borel and Serre, looked at the situation of a proper morphism, and then instead of this guy here, we take maybe coherent sheaves, again, well, it goes to some alternating sum, maybe the R, F, Ri, F lower star of E, this class. So I won't say too much about this, but again, yeah, you could do this. That's a push forward, but you could also go from K naught to the so-called Chow ring, or cohomology. That's where the topological invariants come in by the Chern character. And then you can do the same thing here. And famously, this diagram does not commute. And the failure of this to commute is the Grothendieck-Riemann-Roch formula. Explains exactly how this fails to commute. Okay, so this is from, it's a Hirzebruch-Riemann-Roch is roughly 1955. This is roughly 1958. So already we had a lot of interesting objects coming in. This new object here, the Chow ring, I will get back to that later. Yeah.
Question. So am I right that up to some extent these K naught groups were invented by Grothendieck in order to prove and even to formulate Hirzebruch variant of the theorem?
No, I'm not sure. I think, in fact, what he was trying to do, if you look at, which SJ is it? 6 maybe? He was trying to make a theory of the Chow ring, as far as I can tell. He was trying to make a theory of the Chow ring which was not geometric. which could be done in great generality. So he looked at K0 and the gamma filtration and tried and proved intersection formulas and that type of thing in that setting. That, I think, was more, I'm not sure, but I think that was really, certainly his interest. Exactly, yeah, where his real emphasis lie, I can't say. I don't know. I mean, he certainly accredits this theory. I mean, he in the paper to the Borel-Serre paper, where they give the proof of Grothendieck-Riemann-Roch, but they attribute it to Grothendieck. He writes an appendix, sort of on the appendix is on Chern classes, which is how you define this gadget. And he uses a symbol for the, he doesn't use the Chow ring. He uses a symbol A upper star to indicate it's a completely general theory satisfying some axioms. And he basically is not quite so positive about whether the theory developed by Chow and Samuel really does this. I mean, it's not quite clear in this, to me anyways, that he's really happy with their theory. So I'm not sure exactly what he had in mind. In any case, that's sort of the beginning of the story. And of course, this naught was also not part of the notation. It was just this. The naught comes later because we want to make this a series of groups. So it's really K. So K equals K naught. Gets extended in a rather I don't know, I mean, looks rather haphazard to me. In a rather haphazard too, things like K1 and K2 using...
K minus 1, I think so also.
Pardon me?
K minus 1?
Yeah, okay, I'm talking about the algebraic theory. Let me stick with this. I don't know what K minus 1 is, so let me leave it.
Okay.
I believe you, but... so this of course is, let's say, via homology of the general linear group over a ring R. So K1 is the abelianization of a ring R, is the GL of R modulo the commutator subgroup. Nice abelian group. And this is just the elementary matrices. And then K2 of R is defined as a universal central extension. So this is the infinite group of infinite elementary matrices. So an elementary matrix is the ones generated by those with ones down the diagonal and some non-zero element somewhere else. You have the typical E, let's say, alpha beta of lambda, which has ones down here and a lambda in the alphth row, betith column. And so you can put E of R back here. And then in the middle, you put the Steinberg group, which has generators, formal elementary matrices, modulo sort of three obvious relations that these satisfy. Right? This is the group generated by these symbols, modulo three kinds of relations. So for example, you think of this as a row operation, and if you do this row operation in the same spot on the same row twice, it's just, with respect to the sum, right? If you add lambda, this adds lambda times the betith row to the alphth row, I guess. And if you do it with a mu, then it's just the same as doing it with alpha plus mu. And of course, if the two rows have nothing to do with each other, then the two operations commute. And finally, you have a rather surprising one that if you first do it to the gammath row to the betith one and the betith one to the alpha one, it's like taking the commutator. The two different ways of doing that is just given by a product. So those are the three relations. And then the kernel of this, you can of course send x alpha beta lambda to e alpha beta lambda, and the kernel is exactly this group. And this turns out to be the universal central extension of ER. So it has again something to do with the cohomology of the group. with the homology rather of the group. So this is sort of H1. This has to do with an H2. Yeah, and then you can make some thing having to do with H3. K3 has something to do with an H3. And after that, it gets too complicated. So yeah, there are lots of people who did this. I think of Bass as one of them, but there were lots of people working on this. So this was maybe development already in the 60s. But finally, yeah, so in terms of my own contact with the subject, this maybe started before I was mathematically born, but it was the first thing I really became aware of was, yeah, Quillen. So around 70, the published paper is in a conference from 72, so somewhere in this range, came up with a bunch of definitions of higher K theory. So this is, the first definition was for rings. For R a ring, then you had Kn of R defined as pi n of a certain space. You take, again, it's based on the general linear group of R. So you take, these are, in other words, you take n by n invertible matrices, but let the n be arbitrarily large, and you put, the smaller one and the bigger one by adding a bunch of ones down the diagonal. That's how this group is defined. Then you form the classifying space for that. That's simple. It's a general construction for any group. You can form a classifying space. And then you do something funny. This is the Quillen's plus construction. So this, yeah, if without the plus construction, topologically this space is pretty easy to understand. It's a connected space. Pi 1 is just the group, GLR, and it doesn't have any higher homotopy groups. So from the point of view of homotopy, which is what we're doing here, it's rather uninteresting. So Quillen said, well, we don't want this non-commutative group for the pi 1. We want this group for the pi 1. And we're saved by the fact that the commutator of ER with itself is itself. The ER is a so-called perfect group. So he showed how if you have a group and a perfect normal subgroup, you can form a new space. I mean, if that's pi 1 of some space, you can form a new space by killing the perfect subgroup and leaving the homology of the space the same for all local systems. And that's this thing. That's what this does. Kills the elementary matrices in pi 1. So pi 1 becomes exactly K1 by construction. And then the homology is the same as GL homology. So if you have something defined in terms of homology of GL, it should also be coming from here. And that's in fact why this is a reasonable definition for n equals 1, 2, and 3. It recovers the old definition from that universal property. But then for the higher ones, it's rather mysterious.
May I ask you?
Yeah, sure.
Yeah, so what would do we know the answer for K1 of, say, of a field?
Yeah, that's easy. Oh, you want to?
No.
You're asking me. Yes.
Yeah.
Yes, and the answer is yes. We know. And of course, everybody knows this from. Yeah, I should have said this. Thanks for bringing this down to earth. Of course, K1 for a field is just the units in the field by the determinant, because we all know that we can always, by row and column operations on a matrix, we can change the matrix, an invertible matrix, to certainly a diagonal matrix, and then it's a little less obvious how you can move one diagonal from one position to another position by you just get the determinant in the 1 by 1 spot and ones elsewhere. But you can actually do that. But that's a little exercise in elementary linear algebra.
K2 of a field is already...
Yeah, K2 of a field then is the theorem of Matsumoto.
It's tough.
Yeah, it's tough, yeah. Not so obvious, although it has a presentation, so maybe I should say that. Yeah, so maybe it's a good point. K1 of a field is equal to the units by the determinant map. And K2 of the field has a presentation. It's the unit group, tensor the unit group as abelian groups, modulo the two-sided ideal generated by symbols of the form A tensor 1 minus A. So it's a Matsumoto presentation. Okay, but Quillen, in fact, just having this description for a ring R, there were other definitions of K-theory of a ring R due to Karoubi-Villemayor or Volodine or Koine had an interesting definition. But what made Quillen's construction really work is he actually defined it for E, an exact category. So I won't give you the full axioms what an exact category is, but these are examples. Category of vector bundles or a category of coherent sheaves. It's a reasonable additive category having a notion, good notion of exact sequences. And then he defined Kn of the exact category by making a new category, Q, probably for Quillen, of the category. Then taking the, maybe I'll call it B. If you have a category, you can form a space, the classifying space, or the nerve of the category, another name for it. Then you essentially take loops in this, so I'll just say pi n plus 1. And this, okay, so this definition is actually for n equals 1, 2, etc. It omits the original start, k0, but this definition actually works for n equals 0, 1, 2, and recovers k naught of E is the Grothendieck group K of E. Grothendieck group construction. So it's exactly right for k naught. Okay, so, and then there are other definitions of K-theory, also similar types of categorical or simplicial definitions, Waldhausen K-theory and various other definitions. I'm not going to get into that, but the point is that K-theory is ubiquitous. K-theory is a functor in this setting from exact categories to, graded groups, if you like. So K-theory is a functor. Anytime you have an exact functor of an exact categories, you get induced maps on the K groups. And in these examples, for example, if you take vector bundles on X, for example, if you take F from Y to X, a map of varieties, that induces the exact functor F upper star from, P for the category of vector bundles on X to P the category of vector bundles on Y. So you get an induced map, F upper star, on the K groups of X, defined as the K groups of the category of vector bundles on X. So you don't have to do hardly anything to get a nice functor.
What if we have right exact function? Not exact, but only right exact.
Yeah, then you're in trouble. Then, of course, Quillen in this paper in 72 had a number of ways where you could get around that problem. For example, what about the push-forward map? The push-forward map here is quite problematic, right? Push-forward is good for coherent sheaves, but it's not exact, right? It's left exact. Yeah, so what do you do? Well, I mean, what you did here was you take an alternating sum. Quillen said, we don't do that. We do something which is equivalent to that. We pass to the subcategory of things for which the push-forward functor is exact and hope that that's good enough. And he proved, gave statements and proved theorems which made precise when that was good enough, and in this setting it is good enough, and gives you a nice push-forward functor for proper maps, assuming that the X was smooth, and for that you needed because then you needed the resolution theorem, which tells you when you push forward a vector bundle, it's no longer a vector bundle, it's just a coherent sheaf. You have to replace again the coherent sheaves with vector bundles, and that's he enabled that with his resolution theorem. The third, so that's two of the important theorems. One very important theorem that he proved was the so-called localization theorem, which enabled you, in the case of exact categories coming from abelian categories, to take break up the K groups, put them into a long exact sequence involving an abelian category, a Serre subcategory, and the quotient category. So this was quite useful. Okay, so when you have these theorems, a resolution theorem, you had the localization theorem, and you had the so-called Dévisage theorem. These two kind of come together. What that does is it makes K theory of, say, category of coherent sheaves equal to K theory of vector bundles if you're on a regular scheme, or say smooth varieties. And that's the, say, resolution theorem. The localization theorem and the Dévisage theorem make K theory into a cohomological functor. In other words, if you take the K theory of a scheme, K theory of a closed subscheme, and the K theory of the open complement, you get a long exact sequence which relates the K groups of those three things with another. Okay, so this is really what makes things computable or gives some cohomological sense to this in terms of the topology of algebraic varieties. So that was quite important. Another remarkable fact that came out of this very quickly were the conjectures of Lichtenbaum on special values of zeta functions. So there's the classical statement that if you have a number field f and you take the Riemann zeta function of f and you look at, okay, it has a functional equation, you look at it at 0, then this value is built out of a bunch of terms. There's a term, I won't put them all how they fit in together, but there's terms that come in, so it's built out of things like the order of the class group of the number ring. In other words, there's things that have to do with the number of roots of unity in F. And then there's a transcendental part, the so-called regulator, which has to do with how the logarithm of units sit inside of a hyperplane in the space gotten by taking the real and complex embeddings, so-called regulator, co-volume of that. So all these things fit together to give you the value of the zeta function at 0, and this thing has to do with K0, this thing has to do with K1, units, right? This thing has to do with K1. So Lichtenbaum said that in general, let's say that this thing at minus n should be computable in terms of higher K theory of the ring of integers of F. In fact, not just higher K theory, but let's say Kn, and I guess Kn and Kn plus 1. That should be all that you really need. This turned out to be wrong. This was wrong. There's the famous example, I think at minus 1, he was off by a factor of 2. Let's see. Yeah, because it... or minus, yeah, let's see, no, that k, not kn, sorry, k, sorry. This was wrong, that k2n and k2n, let's see, plus 1. Yeah. So n equals 0, you get 0, 1. Yeah, that's right, okay. So for n equals minus 1, you should get k2 and k3. And it was almost right, except there was this annoying fact that the order of k3 of the integers was not, it wasn't z mod 24, it was z mod 48. And the conjecture predicted z mod 24. So, yeah, this suggested, and it was already suggested by, I didn't say anything about this, but there was, you could do this whole story of K theory in the topological setting, talking about, say, continuous vector bundles on a topological space. And there was a close but not exact relation of the K theory with cohomology. So motivated by that, I mean, they were almost the same. They were off by some small primes. And so I think motivated by that, this idea that you should be able to break up K theory into smaller pieces, and it wasn't exactly all of K theory that had to do with the value of the zeta function at minus n, but just the weight n piece. So you should instead correct this by using the weight n piece of K theory. And that's also not so good. It's not really a well-defined gadget. And so you should probably have something that has more to do with cohomology, but with some close relationship to K theory. Now the first, so what's cohomology? For space, cohomology is just the cohomology of the singular cochain complex. So the idea came out that there should be complexes, say for every smooth variety, there should be a complex of sheaves on the variety, so that when you take the hypercohomology, it gives you something very closely to weight n K theory. Here, weight n, you have these additional operators on here, the Adams operations, and at least rationally you can define the eigenspaces for the Adams operations as the weight n pieces. So Beilinson and Lichtenbaum had sort of two complementary conjecture the existence of complexes that would give a good integral replacement for this idea of weight n K theory. See, the problem is that the weight n K theory you could only define really after you want eigenspaces, and for that you have to pass to rational coefficients, and then you lose a lot of interesting information, especially counting elements in the torsion group. You lose that information, so it's not such a good idea to do that. And let me concentrate on what Beilinson said. This was around the early 80s, around 82 or so. There should be a bunch of complexes, a collection of complexes, gamma of n, let's say on x. Should be functorial in x, but this is on not z of n. He called them gamma then. These are just, okay, this is an important point which I'll come to in a minute. These are just some weird complexes. No meaning to them, no real meaning, just like singular cohomology, like singular cochain complexes, right? This is a complex on the Zariski site. Complexes of sheaves for the Zariski topology on X and functorial, contravariantly functorial on X. N should be 1, 0, 1, 2, etc. And there was also, Lichtenbaum gave something for the A tau site. Let me not give those. But there are various properties. For example, the gamma 0 should just be the constant sheaf Z. The gamma of 1 should be GM put in degree 1. And then, okay, so there's a whole other list.
GM is a sheaf of invertible.
Yeah, this is on an open subset. These are the invertible functions on the open subset. O star, if you like. Okay. Then, yeah, so here, these are sort of easy to arrange, right? There they are. The next one is much more difficult. So you have the cohomology sheaves of this complex of sheaves. Maybe I put an R here, or N, why not N? This should be 0 for I, yeah, this is the I less than 1. This is, of course, for N bigger than or equal to 1. And for I bigger than N. This one was okay. This one is still not quite there. Okay, if you take gamma of n modulo an integer big N, this should be quasi-isomorphic to the following thing. You take the sheaf, the atoll sheaf of nth roots of unity, you tensor them with themselves n times, and you take the derived push forward to the Zariski site. And then that's still not enough. Then because of this truncation property, this won't have the truncation property. You have to truncate this in degrees less than or equal to n. If you don't know exactly what that means, don't worry about it. Okay, another property is what's the relation with K theory? Well, these weight n pieces of K theory can be actually defined integrally. This is what Grothendieck tried to do. If you take the nth graded piece for the gamma filtration on K theory in degree j, and then work rationally, this should be the same thing as the cohomology sheaf. Think of this as a sheaf. This is the cohomology sheaf in degree 2n minus j of, no, I mean, maybe this is global. I guess this is global. It's supposed to be globally the hypercohomology in of this gamma n, again with q coefficients. So this is the relation with the Lichtenbaum conjectures, that rationally it gives you something which you should think of as the graded, weight graded pieces in K theory, but it's an integral version of it which should have better properties. And finally, I'll put it over here, when you actually take the top cohomology sheaf.
Am I right that upper state in the last formula, the graded number n?
This is an n. The weight n piece is supposed to be given by the weight n complex. Yeah, thank you. And now when you take the top cohomology here, this is supposed to be a sheaf of Milnor k's. And this is a generalization for a field anyways. It's a generalization of this gadget here. Instead of just taking this in degree 2, you take the full tensor algebra of the group of units, and again mod out by the same ideal here. Okay. So that's what that would be for a field, and then you have to extend it to be a sheaf. So let me not say that. Okay, so that was 82. But then by 1985, Beilinson reassessed the situation and said the following. This is what he called absolute cohomology, because it gives the weight graded pieces of K theory rationally. And that has some nice universal property for so-called Bloch-Ogus theories with Q coefficients. But, and this should have also that similar property. But then Beilinson made the rather astounding reinterpretation of this, that this functor goes to the hypercohomology on X with coefficients in gamma Q. This should be X groups in a category of mixed motivic sheaves on X for the constant sheaf X, or say Zx of 0, against a Tate object Zx of Q. So this should be a category of mixed, an abelian category of mixed motivic sheaves. So suddenly he put these rather ad hoc complexes with a list of bizarre properties into a completely natural context, even though this gadget didn't exist and still does not exist. So it's an abelian category. So this thing didn't exist and it still doesn't exist.
Many people works.
Yeah, many, yeah, but all, okay. So, yeah. So that's first, that's the front of page 1. So I'm going to have to say plus, let me just say plus many other conjectures. Many other properties. So maybe I'll cut to the chase here. I should say, so up to now, you can divide these properties into 2 categories. I mean, one's the ones that are verified and the ones that aren't. But, but that division turns out to be a structural division. There's some properties which just have to do with structural properties in this category and don't rely, would be just as good, could be just as good described by working in the derived category of this abelian category. For example, X groups are shifted Homs in the derived category. So if you have a triangulated category which looks like, cooks like, and tastes like the derived category of this abelian category, you could still define this group or this group without saying that it's X of some objects. It could be shifted Homs of some objects. You could say it has certain functoriality properties if the triangulated category had functoriality properties, like existence of so-called 6 Grothendieck operations. You could have a relationship with K theory, because once you have these groups, then you could ask for a relationship with the K theory. You could ask for a spectral sequence going from these so-called motivic cohomology groups to K theory. So there are a lot of properties which would follow without having an abelian category. One important property which doesn't follow is that in an abelian category, these X groups, XP, are 0 for P less than 0. And that's related to, but slightly weaker than, this property here. This is saying that the X groups would vanish for P not only less than 0, but less than 1. So that's as long as the weight was not 0. So that's an additional property, which, and that's incredibly far from being known. So, like I say, it's divided into pieces. The structural pieces are actually all there, and the non-structural pieces having to do with the existence of an abelian category, which gives you additional vanishing, for instance, are not there. There's another fascinating conjecture that follows from this, where he says, okay, this is the category on X, and you can consider the map from X to a point, and you take the Leray spectral sequence for that. So, by the way, yeah, I should say, for example, other properties, one of them being, so let's call this motivic cohomology of X with coefficient Z of Q. One property is, which is true, is if you take the 2n motivic cohomology of X with coefficient Z of n, this is isomorphic to the thing that I wrote down but never defined, the group of codimension n algebraic cycles on X modulo rational equivalence. And then you take the Leray spectral sequence for X mapping to a point. This gives you a spectral sequence which would converge to all these groups, in particular to this group. It give you an interesting filtration on this group, which would be a finite filtration, and so-called block Beilinson conjectural filtration. Again, because it relies on the yoga of an abelian category, this is not known to exist. Okay, so that's a quick summary of Beilinson's conjectures. the complexes. So what about, yeah, I said almost all these things are in existence. Maybe I'll give you a quick list, since don't have too much time, of how things progressed after Beilinson said this. Well, very quickly afterwards, Bloch, shortly followed by Suslin, came up with complexes that should, for the gamma n, at least maybe Suslin's not for the gamma n, Bloch had something for the gamma n. Bloch had this complex, the so-called cycle complex, Zn of x star. This is built out of, let me not give the definition since I'm really running out of time, built out of algebraic cycles. In other words, thus the free abelian group on subvarieties of codimension n, not on x, but on x cross the so-called algebraic m simplex for varying m. This is just equal to the hyperplane inside of affine m plus 1 space, defined by the usual equation you have for the real simplex inside of real m plus 1 space. And you can set some of these coordinates equal to 0. You get faces on this thing. And this makes a complex which looks a lot like a complex singular chain complex. And this actually turns out, if you define gamma n in degree m to be Zn of x 2n minus m, this has most of the desired properties. The one that failed is this one. This is still not known. But I think up to now, it took a long time, but up to now I think all the other properties are known. This one was, of course, the so-called Beilinson-Lichtenbaum conjectures, which followed from the Bloch-Kato conjecture, and was originally, it's proved when, in 2000 and
Maybe 99 or
99 by Voevodsky. Took quite a long time to do that. That was maybe the hardest one. That's
maybe
For P
yeah.
equals 2.
Well, for p equals 2, it was a little before.
And
Yeah.
n equals 2.
Right? For n equals 2, this is the theorem of Merkurjev-Suslin.
No, I mean n large equals 2.
Yeah, but I don't mean it. I mean little n equals 2. Merkurjev-Suslin back in, when was this? Like 83 or something, right?
Yeah. Okay.
I mean, even before the complexes were there, they had the theorem, so not bad. Okay. Anyways, a lot of people went into that. I want to just make one comment that when Bloch defined this back in, I mean, the paper came out in 85, so he defined it somewhere before that. Pretty much everything in the paper is wrong. I mean, the definition is completely right.
And it was in 86.
What's that?
And it's 86.
I don't think so.
The first one 86, the second one 94.
No. The paper was in 85, and then the second one was in 92. So, but that's something, maybe we're talking about something else. In any case, the definition was right, and most of the proofs of, most of the properties, there are a few of them that are correct, but most of them, there was an unfortunate mistake, which even more unfortunately was very early in the paper. And he fixed the mistake in, I think it was 92, with his so-called moving by blowing up. Maybe it was published in 96, but the paper came out, it was announced in 92. In any case, then Suslin had a similar construction with something which is maybe even more natural. This thing is a direct analog of the singular chain complex. So this thing in degree m is the free abelian group, I'll just write it down because it's so simple, on W closed integral subvarieties inside of x cross delta m such that the map from W to delta M is finite and surjective. So once it's finite and surjective, then you can very easily restrict to faces and make a boundary map by taking an alternating sum of restriction maps. That defines a complex. And he then defined the homology, so which we call now the Suslin homology. And if you take any abelian group A, you just take the homology of this complex tensored with A. And this would be, should be a nice model for some motivic homology. Unfortunately, I mean, the sort of parallel situation, the localization property here, which is what makes this into a homology theory, was the part where the proof was wrong. And similarly, Suslin was not able to prove a nice Meyer-Vietoris property for these complexes. So in some sense, the theory was kind of stuck. It eventually got fixed. Bloch was able to fix his problem with the localization sequence by what is very rare, a completely new method of moving cycles by blowing up rather than the classical method of Chow by actually moving them by more geometric means. And Suslin was saved by Voevodsky. I mean, and maybe Suslin saved Voevodsky, I don't know. There was certainly a very intense collaboration between the two. So Bloch fixed the localization problems by blowing up, sort of an extreme reaction, but that's what he did. And then Suslin's Meyer-Vietoris problem was resolved by Voevodsky's construction of now a triangulated category. I'll just call one of the versions dm of k. This is a triangulated category, which was exactly what was looked for here. Not an abelian, not the derived category of an abelian category, but a triangulated category where one had such objects, these Tate objects, and whereby one could then define motivic cohomology. So one had objects z of n in here. One had for every smooth variety x, or a motive of x, and one could then define the motivic cohomology of x with coefficients, let's say z of q, as just the Homs in this derived category of the motive of x to z of q with a shift by p. And similarly, homology could be defined hn of x, say a, motivic, could be defined by taking Hom in dm of, say, z of 0 to the motive of x tensor A with a shift by n. And it turned out this was one of the main theorems was to show that exactly these groups were computed by Suslin's complexes. So this turns out to be exactly the same as Suslin's homology of x with coefficients in A. And now built into this category is a Meyer-Vietoris property for this M of x, and that enabled Suslin's, showed that Suslin's complexes did have the desired Meyer-Vietoris property. Okay, so I have a few more minutes. Let's go on to some other interesting properties conjectured by Beilinson. One of them was the relation of, so let's get back to K theory, the relation of motivic cohomology to K theory. So maybe Oh yeah, while I'm erasing, let me just say in words, this was defined for a field, but one can extend these definitions for an arbitrary base scheme. Remember what Beilinson wanted was a theory of mixed motivic sheaves over an arbitrary base X. And this is now possible. So we have, in fact, a category X goes to dm of X. Yeah, it's almost okay. It's still, this is still an open problem in full generality. But at least for X smooth over a fixed base field, perfect base field K, we have a nice functor. And this, again, satisfies the formalism desired by Beilinson, the so-called 6 operations of Grothendieck, and this is due to real fundamental work of Ayoub plus some other people. Okay, so that's in terms of the structural story, that's okay. So now let's look at the relation to K theory. So again, Bloch, in his original paper showed that that this motivic cohomology defined. So when he defined it, let me call it his higher Chow groups. This is defined as the HP of these complexes. And from my definition, this is the same thing of the motivic cohomology. It's the same as H2Q minus P. Oh, by the way, it turns out Bloch was right that this does agree with Vojevodsky's motivic cohomology. So we have a nice theory. And this thing, if you take it with Q coefficients, does in fact give you this Qth graded piece of the gamma filtration, and now on Kp. So the 2Q minus P works out then with Q coefficients. So this is okay. But Beilinson asked for more. Beilinson asked for so-called Atiyah Hirzebruch spectral sequence that would integrally give the relation between the motivic cohomology. So it should look like this. So this is the motivic cohomology with coefficients z of minus q converging to the algebraic K theory of X. So this is how we come back to algebraic K theory. And this also has a long story. This was actually constructed, again, in a somehow ad hoc manner, or let's say by hand manner, for X spectrum of a field by Bloch and Lichtenbaum. Again, the main ideas here were somehow an extension of the blocks moving by blowing up construction. And then this was extended and refined by Friedlander, Suslin for general, let's say fairly general X, a quasi-projective smooth X for X general. And there's another construction due to Grayson, which you recently wrote a paper on. And so there's also the Grayson version, which looks quite different. And then there's a version that I want to talk about. There's the coordinate-free version due to Vojevodsky. which works in motivic stable homotopy category. So maybe in the last 2 minutes, 5 minutes, okay, thank you. Let me say a little bit about this. Like I said, these are very explicit complexes, tower of complexes, to give a spectral sequence. Here, by now we have a theory developed by Voevodsky, which at first also the computation of this relied on some explicit work with complexes, but by now it's like in homotopy theory, it's a fairly structural proof. It doesn't really use any, I mean, there's a proof available now that doesn't really use any explicit getting your hands dirty with anything. So some people like this, some people don't, but anyways, that's just to show how the theory is developed. I thought I'd mention this. So we have this category SH of K. I can't say too much about it, but this is a so-called motivic stable homotopy category. This is where, so this is supposed to be a version for algebraic variety that the classical stable homotopy category is for spaces. So the stable homotopy category is where generalized cohomology lives. If you have a cohomology theory in the generalized sense on topological spaces, it's represented by an object in this category as maps into various suspensions of the object. And the same thing is true here. Any reasonable cohomology theory, like motivic cohomology or algebraic K theory, many other theories, are represented by objects here. Here, the theories have two variables. I won't have time to explain why. Here, they just have the usual x goes to, say, E n of x. Okay, and in this category, you have the so-called ordinary cohomology, represented, like singular cohomology of x with coefficients in some group or A. And this is represented by taking E to be the so-called Eilenberg-MacLane spectrum of the group A. And here the ordinary cohomology is motivic cohomology. We've seen that it had A is now, instead of Z, some group, if you like. And this is represented by taking E to be the motivic, I'll put a little mote here, Eilenberg-MacLane spectrum on A. Now, there's a way in topology to break up a complicated theory like K theory into smaller pieces which are ordinary, just singular cohomology, the so-called Polsnikov Tower. And so for E in SH, we have the Polsnikov Tower, which consists, I write it this way, the various connected, more and more connected covers. And if I take this one modulo this one, I get exactly this Eilenberg-MacLane gadget on the nth homotopy group of E. Now for a refined gadget, a motivic gadget, in this motivic homotopy category, we have Voevodsky's version of the Polsnikov Tower, where you have a similar truncation functor and now the so-called slices Sn are Eilenberg-MacLane objects associated, oh sorry, this is with an nth suspension. There's an nth, so-called nth T suspension of something which we can call the homotopy motive of E. So it's no longer a group, it's a motive in this category DM of Voevodsky. So this is in an abelian group, or in the derived category of abelian groups, if you like. And this is in this triangulated category of motives defined by Voevodsky. So both of these give rise to spectral sequences which enable you to compute the E cohomology of some x in terms of, in this case, motivic cohomology, or in this case, in terms of ordinary cohomology, so-called Atiyah-Hirzebruch spectral sequences. That's why Beilinson called it that. So, and this is, in the case of K theory, so the computation that you make, the computation is that the homotopy motive of algebraic K theory is just z of 0 for all n. Just like the nth homotopy group of topological K theory, well, there's a even and odd thing going on here. This is 0 for n odd, and it's z for n even. These are quite closely related topics. So once you make this computation, you get this spectral sequence from the general machinery for free. But then the question is, how do you make the computation? And the first computations were made, again, by grubbing around with actually looking at complexes. But now there's a way to do this. So let me outline how to do this, and then I'll stop. Can I say a word about how to do it, and then let you all go? So how do you do this without getting your hands dirty? So here's the, say, most elevated, but maybe least, I don't know, more transparent, less transparent, hard to say. There's an elevated proof of this computation. How to compute that these homotopy motives of algebraic K theory are z for all n. Well, you start with something which is the algebraic version of complex cobordism, MGL. This is like complex, this is some gadget here. It represents some theory. This represents complex cobordism. This represents algebraic cobordism. And you compute that the first thing you compute is this. And this is equal to just mu 2n. Let's say tensor z of 0. Maybe I should put a z of 0 here. This is a group. This is a free abelian group of finite rank. So I just take that many copies, the rank many copies of z of 0. So how do you, this is the so-called theorem of Hopkins-Morel. They sketched a proof of it, but the details are given by Hoywa. And the proof doesn't use any specific complexes, but it does use, yeah, let's say, knowledge of the motivic Steenrod algebra. Okay, so that's what goes into that. Then you want to relate, let's say, what's the relationship between topological K theory and mu? It's the same relation between MGL and algebraic K theory. This is given by so-called change of, this is the Landweber exactness. It's given by change of the group law here by a Landweber exact group law. So it's the theory of Landweber exact formal group laws, which was developed in topology as a way of starting with complex cobordism and constructing lots of new theories from it. It works just as well to construct algebraic K theory from algebraic cobordism. And once you know that, then you have, in fact, yeah, once you know how to construct this from this by changing So mu has the universal formal group law. That's why you start with mu here, and it has the same formal group law as this one does. Once you know that, you get the K theory by replacing the universal group law with the so-called multiplicative group law. And that turns out to be a Landweber exact group, so this works just fine. And then you use a general construction of Marcus-Spitzweg, which computes pi mu n of E for E a Landweber exact theory. And again, this is completely general construction, and it yields the desired result. So since I've more than run out of time, I can't tell you the last chapter of the story, which is still open. So I'll just say it goes back to K theory, because K theory, as I said, is defined for everything. For example, for non-reduced schemes, whereas all these gadgets here, the beautiful motivic theory, doesn't tell you the difference between a non-reduced scheme and its reduction. And so in an attempt to try and get a handle of what happens for non-reduced schemes, Bloch, Hainaut, and other people have defined new cycle complexes, again by hand, which gives some handle on what's going on for non-reduced schemes. And the categorical theory underlying that is a complete mystery. So I'll leave that to you, to the future, to figure out. So thanks very much.
Any questions or comments? Maybe I will make a short comment or maybe very simple question. So what is K2 of a finite field?
0.
0. Very good.
Any other questions?
Yes. And also, what is the name? So pi and K top is this and that, 0 and z.
Yeah, that's Bott periodicity.
Yeah, this is the
famous Bott periodicity. Thank you. Yeah, that's right.
And yeah, maybe in all other questions I will ask. Okay.
Yeah.
Just a small question about the chain complex. Susskind chain complex. Do you have like a co-multiplication or weak co-multiplication on this chain complex?
I don't think so. Co-multiplication? In general, no. But if you have a, well, I think the problem is, right, that the chain complex on a product is not the tensor You don't have a Kunneth formula.
Weak one.
You do for so-called Tate, if the objects are Tate objects, like projective spaces, Grassmannians, then you would have that, yeah. So that's a general, essentially the things which are, yeah, cellular, in other words, built like Grassmannians are out of open cells. So you have a stratification, the open cells are affine spaces. Those certainly behave very much like their topological counterparts. And then you do have a Kunneth formula. If you take something built like that and you cross it with anything, then the motivic cohomology, and I guess, not sure about the homology, but I would guess it's true, would, there you have the different weights, then it's not so clear, right? Certainly for motivic cohomology, then you have a Kunneth formula. Whether that works in the homology without the weights,
So
I guess that's okay, yeah. That's true, I suppose. Yeah, sounds good. So yeah, then it should be good, yeah. So for those special types of varieties, you'd have a co-multiplication, like for projective spaces, Grassmannians, quadrics, over a algebraically closed field, split quadrics. But if they're not split, then you don't. So even for very subtle things like Severi-Brouwer varieties, then you don't have a Kunneth formula. So it's a rather rare but welcome property.
Maybe I will make just a short comment. So there was somewhere flying around category of mixed motive, which was supposed to be not defined but to be abelian, and there was some formula concerning x and some vanishing as a consequence, some vanishing of certain x groups. Yeah, and point is that if someone will succeed to prove this vanishing, then lots of concrete geometric application will come. Geometric means to algebraic geometry. some very simple and absolutely unapproachable questions will be solved. So,
So, yeah, now it's up to you.
So another comment that you can easily write down some definition of the mixed motivic sheaves, but you have no idea how to prove this abelian category.
Yeah, yeah.
so